Hello! Today I continue to talk about chemistry, its scope and some branches. Although atom means uncuttable, atoms are cuttable. Even armchair speculation leads to that conclusion. For the existence of different types of atom implies the possession of different structures. So, with sufficient ingenuity, it's likely that an atom can be blazed apart and the so-called subatomic particles from which it's formed identified. Experiment confirms this speculation, and we shall see something of the interior of atoms and thereby the origins of their different personalities in chapter 2. It's here that chemistry draws most strongly on physics. For physics unraveled the structures of atoms, and chemists use this information to account for the molecules they form and the reactions they undergo. That last remark hints at the scope of chemistry. It implies that to understand chemistry, it's necessary to import concepts from physics. That is indeed the case, and chemistry draw heavily on numerous concepts developed by physicists. In return, we, chemists, provide the matter for them to conjure with. Among all these traits, there are two hugely important imports. One relating to the behavior of individual atoms and their subatomic components, and the other relates to Planck, that is, tragically large versions of matter, such as chunk of water or a block of iron. More technically, these are the microscopic and macroscopic worlds, respectively. The crucial import from physics to account for the properties of the microscopic world of individual atoms and molecules is quantum mechanics. Although much of chemistry was developed during the 19th century, there was little understanding of why some things occurred and others did not. At that time, Isaac Newton's classical mechanics, the mathematical procedure for accounting from the motion of bodies, was king, for it was so successful at accounting for the orbits of planets and the flight of balls, and there was the expectations that when planets and balls were slimmed down to atoms, explanations of chemistry would be found, and Newton's domain would encompass chemistry too. Newton's fruitless focus on alchemical manipulation was perhaps a sign that he thought so too. However, at the end of the 19th century and early in the 20th, it was found that this slimming down of planets and balls to atoms resulted in the complete failure of classical mechanics. Even the concepts on which Newton's mechanics was based crumbled when applied to atoms and their constituents. Such are the dangers of uncircumspect extrapolation. Then, early in the 20th century, around 1927, a new mechanics was born that has proved to be hugely successful for explaining how atoms and subatomic particles go about their business. To this day, the theory, quantum mechanics, has not been superseded in predictive power and numerical precision. That is, remains largely incomprehensible in admittedly an irksome deficiency. But, in due course, I shall do my best to distill from it what is necessary for understanding the behavior of atoms and hence the whole of chemistry. We shall see that when chemists stir and boil their fluids, their coaxing atoms to behave according to the weird laws of quantum mechanics. The other crucial import from physics is, in this case, to account for the properties of the macroscopic world of blank matter, is thermodynamics. Thermodynamics is the science of energy and the transformation it can undergo. It arose in large part from the Victorian era's depends on the steam engine for driving society forward both literally and economically, but soon proved to be a key part of the fabric of chemistry. The material fabric of our subject is atoms, but the changes they undergo are under the control and impetus of energy. We shall see that not only is energy released when a fuel burns, an obvious, useful, but primitive aspect of the involvement of energy with chemistry, but also that it governs how atoms behave in general. What structures they can form, and what changes in organization they can undergo, and at what rate those changes can occur. Energy also is a subtle way turns out to be the driving power of chemistry in the sense that reactions are impelled forward by it in a manner that I shall explain in chapter 3. Because energy is so intimately coded into the very structure of chemistry, it should not be surprising that thermodynamics play a role despite its engineering origins. Thanks for watching.